Hello, everyone, again. This week we will be continuing on our discussion on our introduction, actually. Last week, as far as I remember, we stopped somewhere around here where we have seen that there's a structure called cell, which can combine different types of data into just one, which encapsulates them. And I've told you about the conditional stuff and looping mechanism and Matlab will be to today's discussion. So, well, most of you are probably familiar with the if condition, but basically what if does is it checks a condition. It needs a condition. Depending upon that condition, it may run the code here, or it may jump to this else condition, for example. And this gives us the capability of branching. It is called, the technical term for this is branching, which is actually not a good thing for computational purposes, because this slows down your computer. It takes quite some time to make this comparison. And if you consider that there are multiple conditions to check, this becomes a pain. But since we are learning Matlab, since we are in an environment where we try to prototype things, dive deep into theoretical stuff or scientific calculations, we don't really have the consideration about the timing of our code, how fast and optimized it is. So we don't really care about that here. So it's also not that big of a deal for that reason. Now, let's talk about the if condition. Now, let's say we have I equals 2, and we are checking the condition if I is equal to 2. And we end this. So what really is necessary is that you just get the idea of if, because this else if else is not really relevant. It's just a shortcut. What I mean by that is the following. If you have, for example, this, and you just display, let's say I is equal to 2, let's say, then you don't really need to know the else condition, because you can take the inverse of that condition. If I is equal to 2, display that I is equal to 2. Otherwise, this is basically otherwise. So this is basically, if I copy this, it is the equivalent of else. Of course, it's really easy when you have just one condition and it can be reversed. So that's not really a big of a deal. But what happens if I have multiple conditions and I'm checking them? Well, then it gets a bit more messy, because I have to have this one, I1 is equal to 2, and this is the AND operator, and I2 is equal to 2 is just one condition. What else here means is that I'm just copying this one here and here. So all the other possibilities. So the first one is not equal to 2, but the second one might be. So let's have that. The first one is equal to 2, but the second one might not be, or none of them are equal to 2. So this is kind of I is not, you get the idea here. Now, basically, if I write down else, I can just get rid of this whole mess, because I don't really have to check every other condition and then OR them with this operator or operator. But if I, for example, pick one of the left or remaining conditions, let's take this one, for example. And if I check that, if this is happening, and since I have checked that already, I can get rid of this. then this is the equivalent of else if. So else if this else is again this condition where everything other than this condition might happen. So you get the point here. We have multiple conditions, we check them, but we have to be careful because else if picks from the remaining possibilities or conditions rather than checking also the first one here. So if you're concerned with the different possibilities, then what you can do is you can just bind the if conditions using else if, and when you're lazy, you can just leave out one possible last condition to check and call it else, or you might check for anything else and use else. It depends on you, but if you know the if block, how it works, you can just use if else. It's pretty much straightforward. The only thing that is important here is that I have to note that this is actually a logic operation. Here we have a comparison operation. So the CPU takes I1 and the value of I1, and it takes the value 2, compares them logically, and returns false or true if they're identical or not. It can be bitwise here, so each bit should be equal to the other one. So yeah, it's kind of an XOR logic gate as far as I'm remembering it. So, and then of course there's this second comparison here. If this is true or false, it is important. And since this is an AND operation, both of them should be true in order to get through. Otherwise, the result would be false, and this condition would not arise. So it is important to note that there are multiple comparisons, and they will be operated with the AND operator, for example. The AND operator will be applied. So therefore, everything should hold. Otherwise, this will not happen. So therefore, if I want to write a trivial if block, what I can do is I can just go ahead and place true here. And if I run this, you'll see that it'll just work. So this is the equivalent of not using if. So these are basically the same. If it's true, then the block is not ignored, it is executed. But if it's false, then the equivalent would be just empty code because this line is empty, so therefore we have no code whatsoever. You can see that when I run it, the if block itself is not executed. So we are kind of trying to write different pieces of codes for different conditions. And one example might be the following. Let's have I equals 1. And as long as I is less than 10, I might want to display I. So this might be a condition that I care for. Of course, I need to display I on its own, the value of I, not the character I. You can see it is 1. What happens if I, for example, display I and increase I by 1? So if I run it again, nothing will change, obviously, because, yeah, it just increases I. I is equal to 2. It's not really that important. But what happens if I copy and paste this multiple times? Maybe a bunch of times. Lots of if blocks, they are just copied and pasted. What happens if I run this code? Any suggestions? What will we see? Or what will be the value of I?
It will print until I is bigger than 10.
Yeah, if for the last case, it will probably check for 10, 10 less than or equal 10 will give us true, it will increment it. It will become 11. But once it's 11, it will not going to enter this if. But even though I've just copied and pasted a bunch of if blocks, the value will not change. So let's run it, for example. So it counts up to 10. When it becomes 10, we are not displaying it. Therefore, I stays 11. So the value of I is 11. But you get the idea here that actually 10 of them might be necessary. Let's say approximately this amount of if blocks may be working, but the remaining ones are just skipped. So what is this block actually? This is not an if block. This is an implementation of another block that we will learn here. It's actually called the while block. So we've talked about the if block, but if you copy and paste it a bunch of times, it will become the while block. If you copy and paste it enough, it will become the while loop. So the while loop is implemented. Let me just get rid of this, like this. So since this is the equivalent, let me just place it here. So you don't have to copy and paste this if block too many times. You can just place just one if block, and the part that you want to copy and paste, you can just call it while instead of if, and you're good to go. So it's basically a consecutive executed if block. It will be executed until this condition is not valid anymore. So therefore, of course, we need a starting point for that. I is equal to 1, but we have to have a stopping condition, or a condition that we will break upon execution of its inside. So this should break the condition eventually at some point. If it doesn't, it will work forever, because you will copy and paste that if block forever. So you have to be careful working with loops. And this is called a branch because it kind of has different possibilities as an outcome. But this is called a loop because the branching goes back to its starting point. Once that branch completes its cycle, once the cycle is broken, we'll continue executing our code as usual. So this is kind of the way it works. We go and execute this line. We check this condition. We execute this, go back to this condition, execute this, go back to this condition until this condition is has become invalid. Then we go on executing the remaining part. But if that's not happening, then we are in an infinite loop. But other than that, we have just a looping structure. And the behind the scenes code that is generated for that, if we would have been in C and looked at the assembly version, we would see that there will be a similarity between the if block and the looping structures. So there's a similarity, but multiple execution of if blocks can generate the while block because we have the same jump. This jumps to outside of the actual block, but this jumps back to its condition, so we can loop with this. We can count with while loops. We can loop over a vector using this mechanism here. Of course, if you code for a small time, then this while loop might look relevant, but all the other coders here would argue that there's a for loop, which is way better. And I would say the same because this looks a little bit crowded here. We have a starting point, we have a stopping condition, we have an increment. But for the loops, this is kind of standard. So therefore, there's a more compact way of doing this, of course. And it's actually not really a for loop in Matlab. It's more of a for each loop. So let me show you what I mean by that. So we have basically the same structure here. We can actually write a for loop that is kind of similar. It starts with 1, it has increment 1, and we will stop at 10, for example, for this example. And we can just get rid of the whole definition in one line. Then we can just place our implementation. And this is basically almost exactly the same. I say almost exactly because this is actually not the for loop. This is actually a for each loop here. So let me just comment this out. Let me show you how it works. So we have 1 to 10. So it counted twice here, 1 up to 10, 1 up to 10. So it is basically the same result. But if you look close to this, you can see that this is actually not a piece of code that assigns I to 1 and then increments it by 1. This is actually the vector containing all the possible values that would be generated in this while loop. And we are actually defining a element, E, and the vector here is given. So therefore, this is more of a for each loop, if you know a for each loop for a different language. Then this is the Matlab equivalent. So the while loop exists, but the for loop is actually a for each loop. You provide a vector and it'll just cycle through each element. So this means that I can do fancy stuff with it. So I don't really have to provide any increment at all. I can just provide a random vector. And you can see 2, 3, and 20, they are all printed out because this is a for each loop. It's not really a for loop, but you can use it as a for loop because we have a colon operator. So 1 with increment 1 up to 10, this can generate me an increasing vector here. And I can toy with it, of course. I can change the increment value, 1, 3, 5, 7, 9. I can change the starting point, the ending point, etc., etc. This is just generating me a vector. And if this is the vector that I'm interested in, or if these are the indices that I want to try or I need for some reason, then you can do it with this colon operator. So it's more of a for each loop, but since we have this operator that generates us the series that are necessary, we can kind of work our way around so that this is also can become a while loop. If we change the value of I to 10 or more, it won't break, correct? What do you mean by breaking? So in the case of for loops. So we have this for loop here, and we have this while loop here. Yeah, I kind of didn't understand your question, I guess. If we change the value of I to 10, it won't break in the case of for loops. Again, so do you mean assignment in the for loop, for example, 11? Yes, okay. Well, yeah, this is an interesting thing. Let me just comment out this one here. So as you can see, it's not actually, and as I've told you, it's not actually a for loop because this would happen. This would break the while loop here. If, for example, I assign it to 11, let me get rid of this. You can see that it executes one time, and since at this point I is equal to 11, it breaks this condition, so we are out of the loop. This is also the reason, and thank you for your question, because it's a nice question here in this case. This also demonstrates the fact that this is not a for loop. This is a for each loop, because it doesn't care about the local variable I and its value. It just cares about the vector that's on the right-hand side here on this line. So it'll execute for all the elements of the vector, no matter what. So you're just overriding it, but it will become, again, it will be overwritten again in this line. So it is a for each loop, and assigning I will not break the loop at all. Yeah, this is basically important, but most of the time when you have a vector let's say 1 up to 10, or let's have two increments up to 20, you can use this loop a bit more interestingly, I'd say. So let's just get rid of this. This is a for each loop. So let's have a vector of certain elements, and let's use this I as an index, and we start from 1 up to the length of x, and we can display, for example, something like this. So let's say the ith element is xi, so something like this. And let's execute this. Of course, I didn't, yeah, this was my intention. There we go. Here, most of the time throughout the course, maybe, for some reason, we will use this a lot because we have like 10 elements in this array. And the first element is 2, the second one is 4, third one is 6, etc., etc. It is possible to use this kind of approach for actually the C version, where we just use I and access the element I. So it would be more like the ith element of x. So we have this for loop in C, int I equals 0, I plus less than or equal of the length of x. You have to have this definition, or you should know the size of your vector and do something with it. I don't know, maybe printf. That would be the equivalent of this code here. So printf %d, it is %f, and then I comma x, something like this. You get the idea. Maybe a new line here. This would be the C code that is used a lot. You start with an integer I, you increment it to the length of the vector that you're interested in, and then you increment it by 1, and you display all the elements of the array with its indices. So you can do that here. You just have to use the vector's length, I, it becomes the index, and you can just display this here. Or alternatively, you can just say, okay, I'm not really doing that. I'm just taking elements from X, and I'm going to display that. So you can also skip that, display each element, and that's it. As you can see, it works, but it's not quite the same. If you're just interested in the values, then you can do this. But for some reason, or for an example, you might also have another vector that you want to fill out with relational data. Then you might need this approach here, because you can access each corresponding elements with this index. What I mean by that is this. For example, I can say x2's elements should be 2 times the value of this one here. Of course, this might not be like this. This might also be index dependent. Then it makes more sense, because in Matlab, you can just take this and multiply it by 2, and it will work. So in Matlab, you can just do this and say 2 times x, and it will give you the element-wise multiplication, and as a result, the vector of that. So this is not possible in C if you think about it, because you cannot multiply the whole array with a number. And from a matrix perspective, it's also not possible. But it is possible in Matlab, because Matlab tends to be more flexible with data types and their interoperation. Here, actually, what we should do to be technically correct is a dot multiplication. This is the element by element operator. So if you have 2.x, you can multiply it. If you, for example, divide 2 by x, you'll get this error. But if you place a dot, it will take each element and make this or calculate this operation through. So if x is this, it will just go ahead and say, okay, the first element, 2 divided by 2, 2 divided by 4, 2 divided by 6. You can see the result as a vector here. So Matlab is quite helpful in this case. You can do lots of things in different ways, and there is probably a more simpler way of doing stuff rather than using a for loop, but sometimes it's inevitable to use for loops. So that's basically it. Hope that this example shows you the significance of both of the definitions here, because they will become relevant for different cases. Now, we have actually talked about this, and I would say this is all you need to know about the if-else, else-if structure and the while and for loops at this point. Now, let's talk about functions, because that will be the basic Matlab introduction at the end of that. And then we will transition into something else. So now functions are actually quite common in Matlab, and I have shown you already functions like zeros, ones, or there's also identity, and Matlab calls it I for some reason. I would have gone for identity, which makes more sense, but we are writing I don't know why, but yeah. These are functions, and we are using functions in the mathematical sense. We have these brackets here, and then we have some arguments. And when we pass these arguments to this function, we get a result. But in Matlab, there's no limitation to that. We can also have multiple outputs. So before I transition into that, let's say we have a function called area, and it takes 2 arguments. The area of a rectangle, let's say. So this should return basically x times y. So let's say area, or A, equals x comma y. So this is the usage of a function. I call the name, and then I use parentheses, provide the necessary arguments, and I know that it will return me a value. So I need to assign the value of this function, the result of the function, in a certain variable. So I have defined A. So A equals area x comma y. So you take this definition without the semicolon, and you create a script that has the same name as the function has. So if I'm calling the function area, I'm calling the script area.m. And if you're using the classical Matlab user interface, you'll see that it will differentiate between scripts and functions. There will be an fx here to indicate you that this is a function, but I'm not using it in environment, so I have to tell you that. Now here, I paste this usage here. So I will use it like this. I have pasted it, placed the keyword function, and then place end here, and we're done. We have defined our first function. So it's not like C or any other language. It has its own ways here. So we can get pretty much used to it if we know how to use it. But we just copy the usage and use it as the definition. So now when you do the calculation, which is a very basic one, x times y is the area in this case, you don't really have to return A like you would in C or in other languages like C++ or C#, I guess. You don't really have to return it because you have already kind of told Matlab that you will return A. Because you're defining A in this line, this is the equivalent of Matlab of returning A. You don't really need this line. And yeah, it's more compact. You already promised to assign A to a value, and Matlab will return this value. So let's try this out. Let's say 2 times 3. Let's run this. Interesting. So maybe like this. Okay, for some reason, yeah. Okay, there's no problem. Now, we have called this function. It calculated the area of a rectangle with sides 2 and 3, and the result is 6. And it returned us, even though we didn't really write the return statement here, because it is already implied. Now, let's say it also gives me 2 more areas, possible areas. One of them, let's say, is x times x, and the other one is y times y. So why am I defining this? In order to show you that what happens if I want to return 3 different values. So x times y is a rectangle, this is a square, this is another square, and for some reason I want to return this. So in C, you can't really do this. You have to use maybe structs. You have to define a struct that encapsulates these 3 values into just one variable and then return the pointer or the reference to it, etc., etc. So it's a bit complicated. But in Matlab, you can use a different approach, which is basically based on the definition of arrays. You can just define them as an array here. So for arrays, we use square brackets, and then we use comma to separate the elements, and we provide the elements in it. So this is basically an array. If you go ahead and place this here, then you can tell Matlab that I'm not returning 1, I'm not returning 2, I'm returning 3 different values. So Matlab can then return these 3 different values. But if you run the script now, you will not get the 3 values here. And the reason behind that is that you're not requesting 3 values. You're requesting only A, which is the first one here. And that's it. So if you want to return all the values, you have to change it to this. So let me take this part here, place it there, and let's get rid of the semicolon. So as you can see now, the square of 2 is 4, the square of 3 is 9, 2 times 3 is 6. You can see that it returned me A, A1, A2. And let me remind you that these variable names don't have to be the same as here. I can just change the notation and call it again. And you can see A1 is 6, A2 is 4, and A3 is 9. So these names are actually local here. XY is only defined in the scope. A1, A2 is only defined in the scope. But you can redefine it here. You can change the names. You can give it values. You can toy with it as you wish, because this is kind of a component of your code that is reusable, but is local to itself, and it knows only the inputs and the outputs. The internals, we're not really interested in the internals here. We just know, based on the name, what the operation is, what the function does, but we don't really care about the details. So we're kind of the boss here, and this is our employed worker. We don't really know what they are doing, but we just care about the inputs and outputs. So functions are therefore important, because you can break down a complicated project into its components. Maybe the components will also consist of multiple functions, definitions, etc. So it is quite useful. You only have to know how it works, what the syntax is, and the rest is actually just practice. As you can see, we can use square brackets. And if we use square brackets, it has only one meaning. We are stacking elements together to create an array. So we're returning multiple values. If I want to get the values, I can do this. So as far as I know, you can also take some elements, not all of them. You can skip elements. You can go ahead and say, I just want the first one. I want the first 2. I want the first 3, whatever. You can just also specify that. In Matlab, we keep the names of the function files and the function names consistent. They should be the same. Other than that, they are just basically local piece of code. And yeah, that's basically it about functions. You can have functions that take no arguments. You can have functions that don't return anything. But yeah, other than that, they are just functions. So Yes, you can just write these types of functions. There are some examples here. Yeah, let me quickly talk about this. I have actually used today the string version here. If I have a variable I equals 2, if I wanted to convert into a string and maybe combine it with some text here, I can do it like this. And I can display it somewhere or use it as it is. But if I want to use single quotes, I again have I equals 2, but now I want to combine it like this, then what I have to do is I have to define it in a vector, because we've talked about this. ASD, this is actually a vector of A, S, D. It is the same. The shorthand for the brackets and each single quote characters is actually just single quote and the whole word here. So you have to combine them as arrays. You have to treat them as arrays, and you have to convert the value into a character. But if you use this char function here, you'll see that it will not work, because the value of I is equal to 2, but we have a strange looking, maybe an emoji even. But this was not our intention. And the reason for that is that we're actually using the ASCII table here. In the ASCII table, you will have the lowercase a at decimal 97. And for 98, it will be a lowercase b, etc., etc. So you cannot use char. You have to use a different function, which is called num2str. And if you check the help for it, you'll see that it tells you that it will convert numerical stuff into string. Actually, character representation, but it is called string. It is an awkward naming scheme here, but it is what it is. So yeah, it is str, but it is actually not a string. It's a char. But yeah, if you do this, you can go ahead and run this code, and you can see both are text values. We have converted numerical data into a string or a character array. So we will use that a lot for prints, legends, and plots. So I wanted to show you that. So this concludes the first part of our discussion of our introduction in Matlab, because this is one of the things that we need to know. Basic Matlab usage, basic programming syntaxes, etc., etc. But there's more to it, because we want to also deal with symbolic expressions. We want to solve equations, linear, nonlinear, whatever. We want to toy with symbolic expressions. Therefore, we also need to learn the symbolic toolbox. And in the symbolic toolbox, or by using the symbolic toolbox, we can do something that we cannot do in Matlab. So I've told you that defining variables in Matlab is easy, but it is based on their value. So if I don't assign it a value, I cannot define it. If it hasn't been assigned a value, it's not a variable yet. So you have to assign it something, maybe a number, maybe a string, character, whatever you can. But other than that, you cannot define X as a symbol. But if you define a symbolic X, then you can see that I can type X and it will return me X. So this hasn't been assigned a value. This is not a number. This is not a variable that we are used to. It's more of a symbol. And I have defined here that I will have some symbols. One of them is X. So what I can do is I can now have some expressions like x squared plus x squared times the sign of x, whatever we want. Now we can define these as we would have written them down on paper using a pen. So it's kind of neat to have this capability. This is symbolic math that we are capable of now. But of course, we need to add things like what happens if I want to have a polynomial. Let's have the most basic one here. What if I want to solve for its roots? I can now define this. And we have a polynomial that depends on x. And I want to solve polynomial equals 0. I want to get the roots of x, or which x's do satisfy this equation here. Well, I can use a function which is, does it show up here? Yeah, there we go. There are multiple solve commands, but one of them is the symbolic /solve. So this is basically the function that I will use. I will provide the equation and the variable. You don't really have to provide a variable if you have just one variable. So you can see that the roots of this polynomial are -1 plus -1i. So if you would have solved it, you would just use b squared minus 4 times a times c discriminant based on its positivity or negativity, or if it's equal to 0. You would determine the type of solution that you have, and then you can just go ahead and write down the solution. Minus b plus square root, etc., etc. You get it. So it does it for us. The symbolic engine, there's a symbolic engine, like a graphical engine, that gets rid of the details of stuff, but we communicate with it, we tell our problem, and it will return us, hopefully, the result that we're interested in. So this symbolic toolbox has its own engine. It's called the sim engine, and you're just giving it the blocks. It will return you the results, hopefully. Of course, it becomes more relevant if we have a higher order here, because at some point we are not going to be able to solve them. Neither does Matlab, seemingly, but actually, this is an interesting thing. It calculates the roots of this, and it will return just the first one, the second one, and the third one. But if you convert it into double, because it's not a double value, you get the numerical value here. Now the roots are 0.77 and this complex conjugate pair. So yeah, x is not something that we have in the actual Matlab programming language. It is a toolbox. Therefore, if you define anything using that toolbox, it will stay within the toolbox. So this is actually not a double value. It's just something else within the toolbox. But you can take that and convert it into double, as we did it with string. We gave it a number, a numerical value, and it converted into string. So the same goes here. You can use double and convert something into numerical data. You can also define symbolic stuff by calling sim as we use double and string. And you can see that it is quite different than the Matlab version. Matlab gives you the result numerically. It does the calculation. But in the symbolic toolbox, you don't really do the calculation at all. And this is because of the problems of precision. When I repeat this using 1 divided by 3, the symbolic toolbox gives me 1 divided by 3. It doesn't do the calculation. But Matlab returns me 0.3333. But the problem is this. What happens if I copy this and multiply back with 3? What do you think the result is going to be? If I hit enter, what number will show up? Any ideas? Anyone? 0.9999. Are you sure? I'm sorry to disappoint you, but this is the result. But what happens if I store this and let's say y, and now do 3 times y, and 3 times 0.3333. Interesting. The value of y is 0.3333, but 3 times y is equal to 1, even though 3 times that is not equal to 1. So which one is correct? There's a problem here. One of them can only be correct. So let's try something else out. You can use format short, format length to show up more decimals. And interestingly, even though if I increase the decimals, it doesn't change. The value of y is 0.33, this many digits, but the calculation gives me 1 instead of this. And if I calculate this, it doesn't change. Well, Matlab is lying to you when it's displaying the value of 1 divided by 3, which is this one here, because it keeps track of these divisions, and this one is a problematic one. And it shows you the accurate result because you are dealing with scientific computation, and Matlab tries to be flexible. Sometimes it'll opt for performance, but no matter what, it tries to keep up with the accuracy of your results. Therefore, in Matlab, this will be the result. But if you use any floating point, you will not get 1 here. You will get this approximation. You will get an approximate result. Only Matlab or the symbolic toolbox or symbolic engines like Mathematica, Matlab, symbolic toolbox, etc. Only there you will get the result of 1. And Matlab does it for you. But on any floating point CPU, you will not get this result. You will get the approximate result. Because it is a pain for computers, for floating point units, to calculate these types of divisions, actually, without losing any accuracy at all. So you can safely use the Matlab calculation. So you can safely divide 1 by 3 and then multiply it with 3 again. You will get the accurate result. But keep in mind that the symbolic toolbox does not show you the approximate value if you're not asked for, and it just tells you that it is 1 divided by 3 and nothing else. So you can go ahead and calculate 3 times 1 divided by 3 and you will get the result. Since this one here is not actually 1 divided by 3. It's not the value 0.33, it is 1 divided by 3. So it can show you the division symbolically. So it's actually a fraction, and you can see it as a fraction. And as far as I remember, there's something called pretty, where you can even show it like 1 divided by 3. What happens if we try sim 2 divided by 4? Well, that's actually easy. 1 divided by 2. It carries out the operations that are not harmful, so you can show it as 1 divided by 2. There's also something called simplify. If it doesn't do it automatically, you can just simplify that. It should be sim 2 divided by 4. It does simplify it. You can force it to simplify if it's possible. But if it's something like 2 divided by 4, it will get rid of the unnecessary factor 2, and you will be left with 1 divided by 2 instead of 0.5. The floating point units are pretty much good in the base 2 numbers, so it can divide by 2 pretty accurately, but 3 is not really a thing that is compatible with our floating point units. So yeah. Now, even though this seems like a good thing, sometimes it may become something really bad, because at some point the symbolic expressions may get out of control, and there will be square roots, e to the power of some things, and sines and cosines and stuff. At some point it will be a painful thing to read, because that is what it is. Sometimes if you deal with complex problems, you will get complex results. Therefore, you can actually do something about that. You can still force the symbolic engine to show you it in digit forms, but it warns you you can use it on your own risk. And sol is not actually 0.3333, but you can show its approximate value. So for readability, this becomes relevant, and even more important, you can do something like this. So x divided by 3 is approximately 0.3333x, whereas converting it into double would not work. You cannot convert it into double because x has no value, x is a symbol, and it cannot be converted into double. If we didn't have x, this would be no problem at all. You can see, of course, format short. Let's reset that back. There we go. You can convert it into double. You can show it with VPA, no difference. But if you have unknowns, VPA becomes the thing that you will use, because only VPA can show you symbolic data kind of numerically or approximately. So this can be helpful if you have problem reading the whole expression. Now, yeah, I have told you that we can use polynomials, since those are just linear expressions. And I have told you that we can use solve in order to solve for that. Let's say solve. As you can see, let me just look like that. There we go, it gives us the result. Now, this is not the only way. We can also look for coefficients of this polynomial. So there's something called coefs. And again, here the symbolic coefs is the thing. And you provide an expression, and it will give you the coefficients here. There we go, 5, 4, 1. Of course, the order is reversed. It is ascending order. So the lowest one and the highest one in terms of polynomial elements here, or powers, actually. So we can use these coefficients, even though these are reversed, because we will be considering control problems in this course, programming techniques in control, so we will still stick to control. And if you remember the TF function here, which we use to define a transfer function, we actually need some polynomial coefficients. If I define something like this, I'm talking about 1 divided by s squared plus 2s plus 3. So it becomes relevant to have a symbolic engine and symbolic capabilities on one side, and also something compatible for our control system toolbox, so that when we are done with our symbolic calculations, that we can convert it into, or bring it to the control system toolbox domain and examine it furthermore. And since we are considering the control system design course, which is probably next semester for you, or maybe next year, I don't know. This is kind of the preliminary lecture for that. So we consider these types of connections, because we will be control engineers. Therefore, we need programming, but for our own purposes. So therefore, Most of the time, if I'm defining a symbol, it will be S because we are considering the Laplace domain. It will be a polynomial most of the time because we use polynomials in the linear control theory. And we define transfer functions as fractions of polynomials. Therefore, it becomes relevant to use the symbolic toolbox. Here, I think about the root tabulation method or the transfer function definition. Therefore, in my mind, as a control engineer, the coefficients, first of all, should be in descending order. So therefore, the highest power term should be the first one, and the lowest one should be the last one. So I can reconstruct the polynomial in my head. If I look at a coefficient list or vector 1, 2, 3, it means that it will be s squared plus 2s plus 3. So therefore, I don't really like the way that coef works here. So let me comment this out. And furthermore, it has its issues because if I run this, I don't really expect 5 and 1 as the vector elements. What I expect is, again, in descending order, 1, since there's no s term, it will be 0, and 5 is the last one. So 105 should be the vector, so I can define it as a transfer function object, for example. Or I'm thinking about the root tabulation method because we use the same there. And even further problems occur when we have, let's say, another symbolic variable. What will be the outcome here? What do you think the coefficients are going to be if the polynomial is s squared plus 5 plus k? What do you think? Any ideas? Bu şekilde çalıştırırsam s kare artı 5 artı k. Katsayılar ne olur? Var mı fikri olan?
Yeni bir kolon sıra açabilir array'e. Belki öyle şey.
Belki
Farklı
matris şekline
katsayılar.
döner.
Yani ya da
taşın, değil
hani
mi? Bir
şey,
satır
evet.
daha.
Hani, aynen.
Başka fikri olan var mı? Okay. Now, since we have a sim engine, a symbolic engine, the data that we provide to it, or the expressions that we create, are actually not expressions at all. We have a tree structure. So it decomposes the whole thing into its sub-elements. And every part here has a different meaning, actually, for the symbolic engine. And the sub parts here are s squared, 5, and k. Therefore, if we call this coef function on this, it will automatically generate us k, 5, and 1 as coefficients. Maybe even 5, 1, 1. So actually not k, just 1. So it could be 1, 5, 1 or 5, 1, 1. One of them will be displayed here. So let's see. Let me just comment it out. 5, 1, 1 is the result, as I've already told you. Why? Because we have 5. This has a coefficient of 1. S squared has the coefficient of 1. There we go, 5, 1, 1. So you might have expected to have something like this. 5 plus k maybe. If you're a control engineer, you think about the S domain, so the coefficients of S, therefore it should be maybe 1 and 5 plus k. Or more ideally, it should be 1, 0, 5 plus k, because then I can reconstruct the whole polynomial, s squared plus 5 plus k, because there is no s term. So there's a way of overcoming this problem because the symbolic engine does not know which is the actual variable or if there's any variable that we should care about, because k is a symbolic variable, s is one of them, so it treats them equally. Why shouldn't it? Therefore, you can provide it a symbolic variable in order to say that you should care only about the coefficients of s. I want the coefficients of s, nothing else. So if you do that, at least it fixes the problem where we have k plus 5. But still I'm not happy because I want to have this descending order and I want to fill the missing coefficients with 0. Therefore, what you can do is you can tell Matlab to look for all the possible coefficients. Now we get the result that we are after here. We get 1, 0, k plus 5. If I look at this vector, I can immediately say s squared plus k plus 5. There's no s term at all. So therefore, we will use this a lot. But if we want to use this, we want to convert it into a double. Therefore, we have a problem here, since k cannot be converted into double, since this is a symbolic variable which has no value assigned to it. So let's get rid of k, because that was just demonstrational. And let's try this out. There we go, 1, 4, 5, which are exactly the coefficients of a polynomial that I'd like to have. Once I've done that, I can just go ahead and say, okay, we have these coefficients. Let's call them coef. I can use this coef vector here in order to define a transfer function. Now I have a bridge between the symbolic toolbox, symbolic expressions that have nothing to do with the control theory. And I have control system toolbox where I can play around with transfer functions, apply step to them, look at their root locus, etc., etc. Now I have a connection between these two toolboxes now. This is important in that sense. Yeah.
Hocam, Türkçe sorabilir miyim?
Tabii.
Normalde mesela 5-4-1 şeklinde tersten veriyordu. Ne oldu da 1-4-5 verdi, orayı kaçırdım.
All deyince aslında benim düşüncemdeki kontrol mühendisliği bakış açısındaki işte en yüksek dereceli terimden en düşük terimliğe sıralıyor. Sonra eksik olanları da sıfırla dolduruyor. Tam istediğimiz gibi yapıyor. All dediğinde orada olmayanları da kendisi dolduruyor. Bir de sıralıyor. Çünkü artık işte S kareli, S'li terim ve şey terimi, sabit terimi olmak üzere sıralayıp boşlukları dolduruyor. Öbür türlü sıralamazsa çok mantıklı olmayacaktır.
Anladım, teşekkürler.
Rica ederim. If you use the third argument using all, it means that it will first look for the highest order term. It will just sort all the elements according to that and fill the missing coefficients with 0. So we have to use the variable and then a third argument, all, in order to indicate that we are looking for this exact protocol. We want to have a descending order, ordered, sorted coefficients. And if they're missing from the expression, just put zeros there. If we don't do that, then the polynomial will change because we kind of rely on this protocol. Therefore, it is important. Since we are control engineers, by the way, I will assume that our polynomials will consist of S. So therefore, it will be the symbolic variable that we will use most of the time will be S, the Laplace domain symbol. So therefore, it's possible to, for example, come up with a transfer function, let's say 4 times S plus 5, and then S squared plus 3 times S plus 3. Let's say we have a transfer function like this. Now, it is not possible to use a step function on it, GSS. Why? Because it's not a transfer function object. It is a symbol. It's just a fraction that has no meaning for the control system toolbox. But what I can do is I can use a specific function called numDen, which is basically taking the numerator and denominator, and it will return them both. Since we have two output arguments, one of them is the numerator, the other one is the denominator. So therefore, I will call this like this. And if you're not sure about it, you can just say help numDen, and it will show you it has two outputs. It is called numDen, and it will just take the expression, decompose the numerator and denominator from a fraction and return them. So let's actually comment this out. If I run this, you can see it took the numerator, returned it to me, took the denominator, and returned it to me. Why did I do this? Well, at this point, the only aim that I have here is to convert them, since they are polynomials, I can skip this part, convert them into coefficients. If I, for example, take the numerator and repeat it for the denominator, I will get 4, 5, 1, 3, 3. The exact vectors that will be necessary to define the transfer function. So ns, ds, and we will see that I have converted a fraction, a symbolic variable, into a transfer function object. And it also indicates that by printing out this message, continuous time transfer function. Now I can use GS to look for the step response. Just for an example. So we have a symbolic variable. We have converted into a TF, and that's basically it. Now think about that. Think about this. We have an open loop transfer function. We apply control to it, or we plug in a controller, take the closed loop, look for the roots, do something with it, design a controller, and once we're done with it, we can convert this open loop into a transfer function. We can take the controller coefficients, build the feedback loop, apply step to it, and see the results. So this is kind of the structure that we have in mind throughout this lecture. Of course, we will also see some other relevant stuff, but eventually this is what we want you to have as available as tools to you. So you should be able to come up with theoretical stuff, use the symbolic engine, use Matlab capabilities, design something, and then also maybe apply the results and see what's really happening here. Therefore, we have 3 different topics here. The first one was basic Matlab usage. The second one was the symbolic toolbox. And of course, there are more to it, more functions. We have shown you coefs. You can use these coefficients to look for the roots here. So you can calculate the roots. If I go ahead and let's get rid of this, look at the roots of the S, we can see that we have basically the poles of this transfer function. Now, if we use ZPK, if you know what ZPK is, it will give us this, but you won't be given the exact results or the exact poles here. You can see the 0, it's 1.25, but the poles are not really obvious here because these are complex conjugate poles. If you use PZMap, it should give you what you want. So PZMap GS, and if you say poles, this should actually give you the result. And there we go. You can look at the poles using PZMap. But if you're on the control, if you're in the symbolic domain, then you can just use the coefficients and then use or invoke the roots function. That will return you just roots. So DS is, by the way, a vector. So you can look for roots of all kinds of polynomials using this. For 4, we know that it is -2 -2. You can just go on with it. It will give you all the roots of this polynomial. And if I look at this polynomial, this is 6 plus 5s plus 4s squared plus 4s cubed plus 4s to the power of 4 plus s to the power of 5. So this is why it is important to keep track of the order. If it's descending order, it is actually the polynomial that can be reconstructed and it doesn't lose its meaning. So there are all kinds of functions that can help you out throughout the symbolic toolbox. And one of the most important ones is actually subs. Let's say we have the controller. Somehow our controller ended up being this here. The closed loop is somehow calculated and it appears somewhere in the transfer function. Now we can decompose it here, but once we try to convert it into double, we'll see that there are symbolic variables, so I cannot convert it into double. That's the error. So if I comment this out, I can see that it works and the num looks like this, the denominator looks like this. So let's say we are considering the root locus of a closed loop. Then what we do usually is plug in values for k. And once I have the denominator here, what I really want to do is I want to substitute in the denominator the value k or the symbol k with a certain value, let's say 1. So what I want to do is I want to go ahead and look at this and substitute 1 instead of k. That would give me 4, and I would get s squared plus 3s plus 4. So how can I do this using the symbolic toolbox? Well, it's called substitution, and the abbreviation is subs here. You give it the expression, so you should give it the denominator. You give it the variable that will be substituted into, and then the value. So let's see what happens. Previously, then looks like this. After substituting k equals 1 into then, this is the result. There we go. It was k plus 3, but you can tell the symbolic engine that you want to plug in a value for k, that is 1, in this expression, and it will do it for you. So at this point, when you have done that, you can just go ahead and, so let's do this. We can just go ahead and convert it into a transfer function. And furthermore, what we can do is we can just go ahead and maybe use a for loop and say the k values that I'm interested in are 1, 10, and let's say 20. And instead of 1, I can use kval. And let's actually write display GS. So you have all the possible transfer functions when you substitute these values into kval. Yeah, and then you can do something relevant. Maybe you want to show the pole zero map of this transfer function. Maybe you want to plot step responses on top of each other, whatever you like. So subs is important, simplify is important. If you simplify, it tries to simplify it. If there's, for example, cosine square plus sine square of the same argument, then this will be substituted or reduced down to 1. Simplify fraction, yeah, if you need it, you can use it. VPA, I have shown you that VPA can make life easier. If you want to see what the approximate value of the expression is, you should go ahead and use VPA. And the second argument in VPA is actually how many digits you want to see. How precise do you want to see it? Because this is called variable precision arithmetic. It has a strange name to it. But all it does is it displays the expressions more readable. And all you need to know is basically that, variable precision arithmetic. It just helps you kind of doublifying the results. Even though if there are some symbolic variables, it will show up like double. There are some functions, and you can just read the documentation, because symbolic expression manipulation at some point needs assistance in terms of functions. You need to look up, how can I get rid of this certain problem? Well, you have to look up. You can go ahead and use help if you want to have a quick recap. If you don't remember something, but you've used it already, you can use help. Let's say help expand, for example. Then it reminds you very quickly and shortly. But if you need to learn it from scratch, I would say you should use the documentation. It will open up this window here where you can get a in-depth documentation, which is basically the same if you Google it. If you write down in Google help MATLAB and expand, you will come to this exact page. And as far as I remember, this page should be available offline when you use the documentation, the terminal of MATLAB. You don't really have to have the internet connection because it's already available on your computer locally, as far as I remember. So, well, I have shown you num then, and there's also an example usage. And our third topic which is important, is the control system toolbox. And I think, and I hope that you have already used it. How many of you have used the control system toolbox or any of these functions you can see on the screen before? Have you ever experimented with the control system toolbox? There's one yes. What about the others? Okay. Maybe. Okay. You don't really have to know them very, very well because, well, you can just go ahead and look the documentation. They have neat examples. But to recap, TF stands for transfer function. It requires you two vectors, the numerator, polynomial coefficient vector, and the denominator coefficient vector. And ZBK, you can use this to extract the zeros, poles, and a gain, but you can also use zeros, poles, and a gain to define a transfer function. SS, steady state, it's not going to be that much helpful, but it is there. Feedback is one of the most important ones because you can use feedback and then let's say 2 times GS comma 1. This would mean that you have a controller with gain 2 and an open loop system in a unit feedback setup. So it's basically calculating the transfer function of this closed loop here, which you can do by yourself too. We know that the closed loop transfer function is 2 times GS divided by 1 plus 2 times GS, and that's it. So feedback kind of calculates this for you, so you can maybe also use this approach here. It's basically the same, but a feedback command does this. Step applies just step into the input. We will talk about this in the upcoming weeks. Step info acquires actually the experimental data here. LSIM is kind of step, but with different inputs. Body is the frequency plot of a transfer function. PZMap displays you poles and zeros of a transfer function. RLocus basically shows you the root locus, the postal fruit locus of a certain transfer function, where you can pick your controller gain in terms of a static controller. And in the PDF, you can see some usages here, but you can very well also look at the documentation here. You can use feedback, get the step response, plot it, and show some results. We have LSIM. And we have a comprehensive example here. Let me just copy it up to this point, paste it here, run it, and talk about it maybe. Here's an extra space. Here's an extra space. It, for some reason, added extra space to it, I guess. There we go. Now, first of all, we defined a symbol. We created a new figure. Figure 1 creates a figure with the number 1. So you can create multiple figures, assign them certain numbers. And CLF stands for clear figure. So if anything is drawn on this figure, it will be wiped out if you call CLF after calling figure 1. And hold on means that all the plots down here in line 12, since it's in a for loop, will be plotted on top of each other. If you don't use hold on, only the last one, where a is equal to 5, will show in your figure. If you want to use that figure and draw on top of each other, you have to enable hold on. Grid on is just to display a grid for more readability. We have defined a vector t, the time vector, and then we have a certain parameter that will take values starting from 1 up to 5. And then we define a transfer function, a very basic one, a first order transfer function that looks like a divided by s plus a. And then we take the numerator, the denominator, and then we use sim to poly, but we can also skip that by using coefs, ds, all, and same goes here. So there are multiple ways of doing it, but I'll use most of the time coefs in this case. So we get all the coefficients, and then we turn them into double, and then create the transfer function. And once we have done that, we will use step, and step will return the output response vector and the time vector. We also provide the time vector, and then we plot it. Now here you see something called display name and line width, and you should check out the doc plots, but when I'm using plot, you will see them over and over again. Here in the documentation, you can see that there are multiple options that we can specify in order to customize the appearance of the plot. Since it's something visual, we most of the time do change its appearance. You can see that there are certain options where you can give the line type, the color of the line, and then also some special markers, colors, even marker indices and stuff like that. There are lots of key value pairs that are available for plot. You can adjust the marker size, you can adjust the marker edge color. So it's quite detailed. And throughout this course, you will get used to it, and I will use it over and over again. So it will not be that big of a deal, I'd say. Yeah, it goes on like that, but it gives you some options that you can see here. Line style, for example, is one of them, and you can choose these lines. You can choose markers, you can choose colors, and it goes on like that. You have some predefined colors, you can give your own colors. Line width is something that I toy around with most of the time, because for visual readability, I increased this up to 2. Yeah, these are the most important ones, I would say, because all the other ones are a bit too much at this point. But yeah, you can check out the documentation, or week after week, you will see that you will just get the grip of it. Now, the display name, the line width, of course, is for the line width of the line, because we're drawing lines with plot. Here we have display name, and we have a legend. So most of the time, the usage of legend is like this. You plot 5 plots, then you give the name. So it's name 1, name 2, etc. But I don't really like this usage, because sometimes the plots may interchange places, therefore the legend should be updated, etc. Instead of doing that, you can give names directly to the plots, and display name is actually exactly that. I convert the value of A, since it changes from 1 to 5. I convert it into a string and assign it as a name to the plot. So I can then go ahead and see which line corresponds to which A value. And then I just give some extra data here. And once I enable the legend by just calling legend show, you will see the following result here. Now you can see, hopefully you can see that in the legend there are values and colors assigned from 1 to 5. So here I can see that, yeah, if A is equal to 1, this blue line is the step response of such a transfer function. If A is equal to 5, we will have this response. And by the way, A is actually the pole of the first order transfer function. So we can directly conclude that if the value of the, if the magnitude of the pole increases, then the system speeds up. It speeds up in terms of settling down or reaching equilibrium. You can see that it goes up and tracks 1 at this point approximately. So it takes almost just 1 second to settle down, or the settling time of the system is approximately 1 second, whereas the other one is up to 4 seconds approximately. So this is a slow responding system, this is a faster system, and as A increases, the system becomes faster and faster. For this, we have used the symbolic toolbox, which was trivial in this case, but still to demonstrate that it is possible to use symbolic toolbox. We have converted into a transfer function object, so control system toolbox, and we have used basic Matlab capabilities in order to create this custom plot. So I hope that this gives you an idea about the Matlab usage that is necessary in this course or throughout this course. Now, this actually is the conclusion for this week.